Hello everyone, welcome back to another physics video. I'm Physics Michael, and in today's lesson we're going to explore the Doppler effect. We'll talk about what the Doppler effect is, go through the equations, and see how it relates to redshift and blueshift. Let's get started. First, let's talk about what the Doppler effect actually is. The Doppler effect is the change in frequency or wavelength because the source of the wave is moving towards you or away from you, the observer. As you can see in the figure, if the source is stationary, the wavelengths in all directions are the same, so the frequency received at all directions is the same as the source. However, if the source is moving, for example, to the left, the wavelengths will change depending on the position of the observer. Imagine you are at point A. As the wave source is moving towards you, the waves get squashed together, so the wavelength gets shorter and the frequency received gets higher. And on the other hand, supposing you are at point B as the source is moving away from you, the waves get stretched out. So the wavelength gets longer and the frequency received gets lower. This is why, for example, a train whistle sounds higher as it is approaching and lower as it is moving away. Now let's look at the equations for the Doppler effect. The frequency you hear or observed, which we will call FO, depends on the frequency of the source, Fs, the speed of the wave, v, and the speed of the source, Vs. If the source is moving towards you, the equation is FO equals Fs times v divided by v minus Vs. If the source is moving away, the equation is FO equals Fs times v divided by v plus Vs. So when the source is coming closer, the denominator gets smaller, making the observed frequency higher than the source. And when the source is moving away, the denominator gets bigger, making the observed frequency lower than the source. Let's do an example. Imagine a train blows its whistle at a frequency of 400 Hz and travels at 40 meters per second. The speed of sound in air is 340 meters per second. If you are standing near the track, as the train is approaching, you will hear a frequency higher than 400 Hz. To calculate it, we use the formula 400 times 340 divided by 340 minus 40. That gives us 453 Hz. And as the train is moving away, we use 400 times 340 divided by 340 plus 40, which gives us 348 Hz. So the sound is high as the train is coming towards you, and lower as it is moving away. Next, let's talk about redshift and blueshift. When we look at the light from distant galaxies, we see that the wavelengths observed are longer than what we measured in the lab. This is called redshift. Redshift means the wavelength goes up and the frequency goes down. Blueshift is the opposite. The wavelength goes down and the frequency goes up. This shift tells us if something in space is moving away from us or towards us. Here's another example. Suppose a line in the spectrum of calcium has a frequency of 7.557 times 10 to the power of 14 Hz in the lab. But when we look at the star, we see it as 7.449 times 10 to the power of 14 Hz. The speed of light is 3.02 times 10 to the power of 8 meters per second. To find out how fast the galaxy is moving away, we use the Doppler effect equation. 7.449 equals 7.557 times 3.0 times 10 to the 8 divided by 3.0 times 10 to the 8 plus Vs. Solving for Vs, we find the galaxy is moving away at about 4.35 times 10 to the power of 6 meters per second. Let's summarize what we've learned today. The Doppler effect is a change in frequency or wavelength of a wave when the source is moving towards or away from the observer. Redshift and blueshift are examples of the Doppler effect with light waves. Redshift means the source is moving away, and blueshift means it's coming closer. The key equations are FO equals Fs times V divided by V minus Vs for approaching sources, and FO equals Fs times V divided by V plus Vs for receding sources. That's all for today's video. Thanks for watching. I hope you now have a better understanding of the Doppler effect and how it applies to sound and light. I'm Physics Michael, and I will see you in the next video.